All right. Welcome, everyone. Thanks for being here. I'm going to talk a little bit about ICESat-2, a mission scheduled for launch next September. So hopefully I'll be here next year and show a video of the launch. So next slide, please. So what is ICESat-2 all about? You know, we have 4 science objectives, and developing, designing a mission is a very formal process. And I walk you through the 4 science objectives real quick to make you understand what ICESat-2 is really all about and why ICESat-2 is the way it is designed. The first, we have 2 ice sheet science objectives. The first one is quantify polar ice sheet contributions to current and recent sea level change, and that was ICESat-1's sole science objective. How do the ice sheets of Greenland and Antarctica change in elevation? From what we learned from ICESat-1 is getting just the large-scale numbers is not good enough. At the bottom here are 2 plots of elevation change for Antarctica and for Greenland. And what we saw and discovered from ICESat-1 was that these areas, these small outlet glaciers at the margins of the continents, this is where the action is. This is where we need to do better than we were able with ICESat-1. So we, the project, together with the ICESat-2 science team, defined a second science objectives for ice sheet. And it's a very long sentence, but the key here is quantify the regional signatures of ice sheet changes. The focus here is on regional. We need to do better, understanding what's going on at the margins of the continents. Very important for the design of ICESat-2. If you go to the next slide, we have a science objective for sea ice. It's very easy in a way, measure sea ice thickness. We have a very good handle on the shrinking Arctic sea ice. We have 30 plus years of Arctic sea ice decline, area decline. But before ICESat-1 really, we had basically no or very little information from submarines, etc. How is the thickness changing? How is the third dimension changing of the sea ice? And for the first time really, when we had ICESat-1, we were able to monitor sea ice thickness changes over the entire Arctic Ocean. Greenland is down here, the Canadian archipelago, and Russia is here at the top. And for the 5 years for which we have ICESat-1 data, the sea ice thickness has changed by roughly 2 feet. Those are significant numbers. And because of these findings, the decadal survey said, launch another laser altimeter. If you go to the next slide, we also have a vegetation requirement, and which says measure vegetation canopy height as a basis of estimating large-scale biomass and biomass change. The largest uncertainties in the global carbon budget are the terrestrial components, and that's where we need to do better. But we are a global mission, so in addition to monitoring the ice sheets, monitoring the sea ice and the vegetation, we also have global operational product of land elevation, atmospheric profiles, and this is an example here from our airborne simulator of ICESat-2-like data for the entire atmosphere. And you can see, we see cirrus clouds, we see stratus clouds, planetary boundary layer clouds there, and then the thin line at the bottom here is a surface. If the clouds are too thick, we obviously, will lose the surface. But this is a global product that we generate for ICESat-2. And then we have ocean heights and inland water stages as well. If you go to the next slide. So with these science objectives, we designed our mission. And the specifications are there on the right side. And in contrast to a 1-beam laser, we now have 6 laser beams. We have them organized in 3 pairs of beams. And the reason for this is, for having pairs of beams, is we need to do the need to be able to extract the cross-track slope from over the glaciers, etc., at the margins of the continent. And with pairs of beams, we're able to do this. In contrast to ICESat-1, we have also a much, much higher resolution. ICESat-1 was a single beam laser. We had a 70-meter footprint and took a measurement every 150 meters. With ICESat-2, we have 6 beams. We have a footprint size of 15 meters and measure every 70 centimeters, every 2.5 feet. So we take a huge amount of measurements with ICESat-2. If we go to the next slide, so how do we get slope, cross-track slope out of the data with pairs of beams? So we have a reference ground track over some, steeply sloped area. This is the reference ground track here. And when ICESat-2 goes over, the idea is that we straddle this reference ground track. So we go over the same track with our 2 lasers, and one is to the left, one is to the right. We know our geolocation very precisely. We know where we pointed within 6 meters, and which is needed to be able to interpolate between those 2 lines and then calculate the elevation for the reference ground track. The next time we get over it, we may be a little bit off to the left or to the right, and we cannot control this so accurately, but we know exactly where we were, so we can again interpolate to the reference ground track, correct for the cross-track slope, and then calculate elevation change for the reference ground track on an orbit-by-orbit basis. Over the polar regions, we have a 91-day repeat track orbit, so we go over the same area every season, so we can monitor seasonal changes of the ice sheets with ICESat-2, something we weren't able to do with ICESat-1. If you go to the next slide. So what will the data look like? In contrast to analog lasers, we have a photon counting detectors. It's a micropulse laser, much lower pulse energy. And what we do is, we are in the digital age now, we count and time individual photons. And here are examples for ice sheets, sea ice, and vegetation. And we have this, what we call a photon cloud. This is 12 kilometers of aircraft data, elevation on the y-axis. And you have, these random noise of photons, which is, solar photons that reach our detectors. But you can also clearly see, the ice sheet surface here in this photon cloud. And if you calculate the histogram between the 2 lines here, which looks like this, you can clearly identify and calculate where the surface is. Depending on signal-to-noise ratios, etc., you may be able to make this, the distance between those 2 lines narrower or broader, depending on what your precision requirements are. So for the scientist, it's a huge, playground where we can, determining how we analyze the data. Sea ice is a little different. We cannot measure sea ice thickness directly. The way we measure sea ice thickness is by comparing the elevation of leads, polynyas, small areas of open water within the sea ice, like here, with the elevation of the surrounding sea ice. This is a lead, and if we calculate the histogram between those 2 green lines, we see this peak here. If we calculate a histogram of the sea ice here, we see a slightly broader peak because, sea ice is rough, it's not as flat as a lead, but we can also determine the difference between those 2 peaks. And this difference is what we call the freeboard, and it's a portion of the sea ice that is above sea level. Knowing the densities of the water, of the ice, of the snow, we can then calculate, convert freeboard into sea ice thickness, and this is how we get, global sea ice thickness from space. Vegetation, this is, we have more solar backgrounds in this image, but you can see, we have a higher background rate, but you can also see the diffuse return from the canopy, where, where the tree is. Then we have a more sharper peak at the bottom from the surface. And this will allow, our vegetation scientists to extract canopy height, maybe even tree type from ICESat-2 data. If you go to the next slide. So where are we? Everything is built, and we make sure it will work. This is just a small video from vibration test. We try to destroy the instrument basically before we send it up into space. And we shake it. We put all these accelerometers on it and just shake every component that we are building. We shake it. We shake the entire instrument. We shake everything to make sure nothing will fall apart when we are actually launching. And if you go to the next slide, and then once the shaking is done, we put the whole instrument into the TVAC chamber. There's a TVAC chamber here. Walls are like this thick, and we pump out all the air, and then control the temperature to space-like temperatures, and again see how does it behave in vacuum, how does it behave under very harsh temperature conditions. And if you build it and you worked on it for so many years, it's a scary thing to do, to put it in a chamber and then hopefully it survives. If you go to the next slide. So, as I said earlier, we are scheduled for launch in 2018. And, we have all these measurements that we are taking and, products that we're generating and distributing via the National Snow and Ice Data Center for public use. If you go to the next slide. But we have also a huge group of people who are not scientists who are interested in the data. Estimates of sea ice thickness, it's way beyond what we need as a scientist. Arctic shipping companies are interested. The US Coast Guard is interested. Marine insurance companies are interested. We had an applied sciences workshop some months ago, and people from Lloyd's in London came by to, can we get the data? Because, Arctic shipping is becoming increasingly, popular. We monitor coastal erosions, something the states of Alaska and Florida are very interested in. Lake, river stages, permafrost, near coastal bathymetry, and we measure all the glaciers in southeast Alaska as well. If you go to the next slide. So, does the sound work? No. It does not work. So this is a small movie. I just let it run without a sound, developed by students from the Savannah College of Arts and Design, their view of how ICESat-2 works. And I just let time run out and enjoy this movie a little bit. It's a single photon trying to make it, leave the spacecraft. What's amazing about this movie, the students made the entire movie with dialogues, music, everything in just one semester. They just came up with this phenomenal product. This is their perception of photons. Some are lost through the atmosphere, so. And here's a part that makes us scientists cringe. It slows down. It struggles to get back to the satellite. And the whole concept is the speed of light is constant. This is how we measure range. And we had lots of discussions with the artists. And they say, well, we need to have some drama in this animation. They think very differently than we do. And I wish we had the sound, but it's very cute. And it gets people interested in ICESat-2, which is, what something like this is all about. Basically, the bottom line is he's making it back. His time must be recorded, and he will become part of the photon cloud. And that's pretty much it. Thanks so much.